Okay, so let's finish off section 4.5. For this problem, I'm going to do null A first. So I've already taken A and augmented it with 0. And now I need to reduce. Shouldn't take too long. 1, 2, 3, 4, 0. Multiply by -2 and add 1, 0, 0. And now we do need to go to reduced echelon because we want to actually find a basis for null A. So this is 1, 2, 0, 4, 0, 0, 0, 1, 0, 0. All right, so x4, there's 4 variables. x4 is free because there's no pivot in the x4 column. x3 is 0. x2 is free, I'll call that s. And x1 is -2s minus 4t. So our solutions look like s times -2, 1, 0, 0 plus t times -4, 0, 0, 1. So a basis for null A, try again. A basis for null A consists of the two vectors -2, 1, 0, 0 and -4, 0, 0, 1. So the dimension of null A is 2. Okay, for col A, I'm running out of space, but don't worry, we've done all the work. To find a basis for col A, we have to reduce A and look at pivot columns and then pick the corresponding pivot columns from A. Well, if you take this matrix up here, just ignore the 0 column, that's A that's been reduced, and we can see that the pivot columns are 1 and 3. And so a basis for col A is take the first and the third columns from the original matrix A. So 1, 2, and 3, 7. And dim col A is 2. And 2 plus 2 is 4, which is the number of columns that A had. So the dimensions do add up. Okay, a couple of basis theorems. The first one makes sense. If you have a subspace of a vector space, H is a subspace of V, the dimension of H should be less than or equal to the dimension of V. All right, and then a very important theorem called the basis theorem says that typically a basis you have to show two things, span and linearly independent. But if you know the dimension of the vector space and you have a set that consists of the size of that dimension, so if you know the dimension is P and you have a set of P vectors, then you only have to show one of those two things. You have to show span or linearly independent, and you get the other one for free. All right, so let's go through the true false. R2 is a two-dimensional subspace of R3. By the way, you should pause this, do it on your own, and then come back and see if you did it right. We've already seen that this is false. R2 is not even a subset of R3, so it could not be a subspace. The number of free variables in AX equals 0 is the dimension of col A. Let's put a false over here, and I'll put a false here because it's the dimension of null A. A vector space is infinite dimensional if it is spanned by an infinite set. This one's tricky. I'm guessing that some of you probably wrote true. It's actually false, and I'll give you an example. R2, which has dimension 2, is spanned by the vectors 1, 0, and 0, y, where y is any number in R. Now that's an infinite set, and yet that doesn't mean R2 is infinite dimensional. R2 has dimension 2. Okay, next one. If B is the standard basis for Rn and x is in Rn, the coordinate vector for x is just x itself. We actually saw this in example last time, and we saw that it's true. The mapping x to xb is called the coordinate mapping. That's true. R3 and P2 are isomorphic. That's true. You take a polynomial, a plus bt plus ct squared, and under the isomorphism, it gets mapped to the vector ABC in R3. Okay, if x is in V and B is a basis of V with n vectors, then xb is in Rn. That's true. You'll get one entry for each of the basis vectors, so that's definitely true. Next one, if there is a set of 7 elements that spans V, then the dimension of V is 7. False. Has to be linearly independent. 2. Spans only half of it. But the next one's a little different. If H is 4-dimensional and you have a set of 4 vectors that span, then they form a basis. That's true by the basis theorem. So H and I are different. Take some time to look at those. One's false and one's true. All right, and now there's some pretty simple, straightforward problems for you to do at home. One's a call A problem, one's a null A problem, and the other one deals with coordinate vectors. All right, that's a wrap.